Hello everyone, and welcome to my video presentation on the Zeeman effect. The Zeeman effect is, in a nutshell, the phenomenon of a single spectrum line splitting into several components when a magnetic field is applied. So first we're actually going to take a few steps back and talk about electrons and spectral lines, because understanding electrons and spectral lines is very fundamental to understanding the Zeeman effect. So we will start out here with the nucleus of an atom and its positively charged protons here in the center. Now, going around the nucleus of the atom, you have its electron shells, or electron orbitals. And we'll call these n equals 1, n equals 2, and n equals 3. Now, these electron orbitals are areas where the electron can exist, and they are quantized. This is important because it means that the electrons cannot exist in between these electron orbitals. So the electrons can exist here and here and here, but they can't exist in this space in between. These electron orbitals are all at different energy levels. So the closer you are to the proton and nucleus here, the lower energy the electron orbital is going to be. So n equals 1 is at a lower energy level than n equals 2 and n equals 3. So when you have an electron here, say at n equals 1, and that electron is hit with a photon, which is just an electromagnetically charged beam of energy, like light, that photon excites the electron. And what that means is it causes it to jump up to a higher energy level temporarily. Now, when that electron falls back down to its original energy level, then it actually emits a photon. And that photon that is emitted at a very specific wavelength and frequency. And that allows us to graph it. So here on the next page, I'll show you we've got a visible light spectrum. So we'll call this 400 nanometers over here, 700 nanometers over here. And you can see here we just have a regular uninterrupted visual light spectrum. But below it, we have this visible light spectrum with these lines. And these lines represent the wavelength of the photons emitted when an electron in the hydrogen atom dropped from a higher energy level to a lower energy level. So, for example, you have here, we'll say that this is a hydrogen atom. You have the electron at a higher energy level, drops down to lower energy, emits this photon here, and that photon is graphed on this quantized visible light spectrum like this. And these lines are called spectral lines. And they work kind of like fingerprints. It's kind of interesting, actually. Every atom releases different spectral lines. So you can see below we have a helium atom, and these are the spectral lines for helium. You can see there's a dark one here and some lighter ones here. And I don't know if you can see too well, but there's some really light ones in here as well. So by using those spectral lines, you can actually determine the chemical makeup of unknown substances based on what kinds of wavelengths are emitted from the photons when the electrons drop from higher energy levels to lower energy levels. So the Zeeman effect comes into play when you have a magnetic field that is brought close to the electron orbitals. So here's our magnetic field B. You bring it close to these electron orbitals, and what that does is it causes these electron orbitals to split into multiple sublevels, like this. So this is still n equals 1, and this is n equals 2, and this is n equals 3, but now there's actually multiple sublevels within n equals 3, n equals 2, and n equals 1. And so now the electron is capable of jumping to different sublevels within each electron orbital. So when you have the electron here, and it can jump, it can go from this energy level here, and it can jump up to 1, 2, or 3, and then drop back down. And that allows the photon emitted to take on a slightly different wavelength and frequency depending on which sublevel of the orbital it jumped down from. And this causes the spectral lines to split. So you have here just a regular spectral line. You've got the atom jumps up to a higher energy level, and then it drops back down and emits a photon. That photon is graphed here as a single line. But then when that magnetic field is brought close to it, the electron is now able to jump up to one of these different sublevels. And so the photon emitted can be one of these 3 different spectral lines. So that spectral line here, in the presence of an energy field here, is split into multiple spectral lines. Now, the distance between the Zeeman sublevels is a function of magnetic field strength. So here we have, again, nucleus with a proton in the middle, and then you have, we'll call this whole thing right here is n equals 1, and this whole thing here is n equals 2. And there's an electron or a magnetic field present, and the distance between these sublevels represents a change in energy. And there's actually an equation that represents that. The equation is written as delta E, change in energy, is equal to mu sub beta times magnetic field strength. So for now, we can kind of just ignore this mu sub beta. That's called the Bohr magneton, and it's a constant for each atom. But it's important to notice the relationship between the magnetic field strength here and delta E. So when the magnetic field strength goes up, magnetic field strength goes up, then delta E is going to go up as well. And so this here, in the presence of a larger magnetic field, these lines are going to be farther and farther apart. So to sum up, the Zeeman effect is just that phenomenon of a single spectral line, like we can see here, being split into multiple spectral lines when a magnetic field is present. And the application for this, it's used a lot by people who study stars, who study radiation from the sun, things like that. What will happen is radiation will be detected from the sun or the stars, and scientists will plot it, and they'll plot the spectral lines, and they'll notice that those spectral lines are split. And based on the distance between the sublevels, scientists can determine how large of a magnetic field is present from the spot that the radiation is being emitted from. And they can do this for MRI machines as well. There's several applications there, but for the most part, it's used a lot in measuring radiation from space. So I hope that made sense for you guys. Thanks for watching my video. Appreciate it, and enjoy the rest of your semester.